I think we have got this going. So I have a small bonus for all of you. And I'm going to share very little discussion with something for a topic that you didn't even pay for in the class. So we always like when you get to learn something that you didn't expect. That you get more product than you actually purchased. So I'll do that this morning and talk to you a little bit and that's mainly in response to a number of questions that I've received about from some of you individually about how to deal with data and stuff like that. So. But first, following on from yesterday, so today I hope to finish by noon. So that's my goal, and I think we can do that. So, but we got some really interesting stuff to talk about today. So one of the questions that came to me at the end of yesterday and said, well, duration models are pretty interesting and stuff, but do we really use them that much? Are they helpful? And so I'm just going to show really quickly. So here's that they can be very, very useful and interesting, and you can study some things. So here's a model, a paper that we did some research where we were looking at reaction times of drivers. So to the onset of yellow signals. So we had a driving simulator, and we had a bunch of subjects, and some of the subjects were distracted on mobile phones while they were driving, and others were not. And some were, and so we wanted to see if their behavior was different when they were distracted on the mobile phone. And so we estimated a model, and the time duration is how long it took to react to the time duration was in seconds, right? And so we would say you're driving along, a signal has changed from green to amber, and how long will it take for the driver to respond to that? So very interesting study. And then further down here, we have another study that we did that has so folks like Haley and the Department of Transport and Main Roads, very interested in, and this one we looked at so how long it takes once an accident happens. How do we model how much time has elapsed before the accident is cleared? And that's very important for transport agencies because we want to clear these things quickly, and we want to know what factors are preventing them from being cleared quickly because the congestion accrues and it builds. And so this was another duration model that we looked at that process. So there are lots of interesting processes that can happen and can be modeled and are very insightful using duration models. So, all right. Before we dive into new material, I'm going to just walk through something very interesting here, new bonus. Yes?
I was thinking to use, in Indian context, there are two things. I was thinking of using theorem model for two things. I'm just going to confirm whether I can use it for that. First and foremost, when there are traffic signals, there are people who would wait for a particular amount of time, and then they would violate that because the amount of time they are waiting, about 5 minutes, 10 minutes, or something.
Perfect.
So
yes.
So that they can use first. Secondly, we can use. I am planning to use it for waiting for NMT, like auto rickshaw, not NMT, like IPT.
Yes.
Intermediate paratransit. Waiting for auto rickshaw. For what time would that person wait for the auto rickshaw? Maybe. There are long lines and they have to wait for hours at times.
Yeah.
So till what time that person would wait, and after what time?
Perfect. Absolutely. So you could have as covariates in that case how many people are in the queue, where you're located in the city, some features, time of day, and other things. So absolutely, the first one, I can imagine you're at an intersection. You can measure the time elapsed sitting in a red, where the failure is someone violating the signal. But you have censoring because you have some people that don't ever violate, right? And so you have exactly the situation that duration models are built for. So absolutely right. Okay. Now, let me find this one, and I'm going to open this one, and This is the bonus one. Okay. So, a model I haven't mentioned at all, but is in the book. And this is, and it's so cool because I'm going to talk to you from this picture. So one of the questions that I was asked of me yesterday was, and a few days is, well, if you do a survey and you have lots of information, lots of questions, and you're trying to make sense of all that, then how do you model it? How can you model it? Because you have so many variables and you don't know where to go. That context is ideal for structural equation models, okay, which we haven't talked about. They're related to seemingly unrelated regressions, but in some ways far more able to do more complex things. So I'm going to walk you through this picture and show you how it works. And the details of this model can be found in our book. And this technique is used mainly by psychologists. So this technique was actually, so they call, and it's interesting, they call themselves Psychometricians. People from economics call themselves Econometricians, and statisticians, and from psychology call themselves Psychometricians. And so this is from that literature, and they actually do things a little bit differently, and they think about the problems differently, and it's a really powerful technique. So let me just walk you through this picture, because the picture tells everything about this, how this technique works. And this also brings into, if you remember in the first day, we talked about one of the anomalies in variables. One of them, and I said this is can be problematic for a lot of people, is this concept of a latent variable. Okay? And that we don't directly observe latent variables. Structural equation models are all about latent variables. Okay? So psychologists that study human behavior and understanding realize that there's lots of things that we can't measure directly. Happiness, intelligence, education. So many things about people that we would like to measure, but we can't measure with one thing. So they're all measured imperfectly, or they're latent. So this model, structural equation model, is, and I'll walk you through it, and it'll make sense. And we've had enough background so that all of this can make sense to you. The way this works is all of these Q's are questions that were asked in a survey. So Q question 4A, question 1C, question 2A, etc. Right? So those are 4 questions. Here's 3 questions. Here's another 5, another 3, another 2, another 4. So the idea is that these 5 questions were asked and intelligently asked to try to understand contracts. So this context was, they looked at it, went to a bunch of construction sites and asked a bunch of questions about safety and how they manage safety on the construction site. And so they asked people who were working on the sites and people managing the sites. And so this was about work site safety. And they were trying to understand how attributes of the company affected the actual worksite safety or risk. Okay? And so these 5 questions that were asked are thought to reflect and get at what contractor management ability is. And that the idea would be that these 5 questions collectively enable you to understand contractor management ability. Right? And what's really cool about these, in the way that these graphs are set up, and these are generated by the software. This is from Amos software, and in fact, I think, Sudeshna, you did some structural equation modeling when we were working together. The idea is that this underlying latent unobserved variable is the thing, the entity, that influences the response to these questions. And that's why the arrows go this direction. So these arrows are the direction of influence. So the real contractor management ability influences the outcome to question 4 and question 1 and 3 and 5B and 6B. And then there's an error term because this question doesn't perfectly measure contractability. It's only approximate. And these are the regression loadings down here. So these are essentially the coefficients that are related. So those are the betas related with this equation. So each one of these is a regression equation. Okay, a simple regression equation. What's interesting is what we haven't seen is these are regression equations on a construct that we didn't observe. So that's what's so interesting about these models. So everything we've done so far, the data we're using are observed. So we have a y. In this case, we actually don't have a y. We propose that there is an underlying y that's latent. It's actually unobserved. And the real interesting part of the model is that now we have these unobserved constructs, and we think that these impact each other. So these arrows are the arrows of the structural part of the model. That's why they're called structural equation models. And these also would have regression coefficients. And so the ultimate outcome, the ultimate y in this model was dispute potential. And contract disputes are horrible in a job, right? They cost sometimes millions of dollars. They delay projects. People go bankrupt because of contract disputes. So you don't want them. They're really bad. So the whole point here was to try to understand how all of these factors impact dispute potential. And so this, so you can see the arrows in this model represent the structural part, where all these relationships exist. And in estimating these models, it's really interesting. So you estimate this. You'd have a picture, and you say, "This is the model I want to estimate." And it's going to say, "Well, how well are all these questions capturing these underlying constructs?" You give the names of these constructs. Only you, as an analyst, know what these questions measured. And then you specify what these relationships are. And you can say, well, let's remove that link. Let's say these. And so what's a double-headed arrow? Endogeneity. Exactly. Right? So you're starting to see this in a pictograph that the double-headed arrow is endogeneity. That risk allocation affects owner manageability, and owner manageability affects risk allocation. And you can specify the model that way, and you can test it. And you can say, well, no, okay, now let's compare it just with if owner manageability affects the arrow only goes towards risk allocation. Let's test that. And as we have on all these models, you can say, well, is that model better than this other model? And you keep checking fit until you get a good fitting model. And so this is a really good way to address that question of when I have a lot of data from, say, a survey, and I'm trying to make sense of it. This is the technique for you. This is a really, really good technique for modeling these kinds of processes. And they give really, really good insights to what's happening and can tell you. This is the first structural equation model I ever estimated. I remember I told you I went in summers, went to courses. So I went to a summer course, learned how to do structural equation models, came back, found a really good problem with a colleague. We wrote this paper, and the year later, this is the first paper I ever wrote that won an award, and we won this big award in construction management, and that was a really great paper because no one had known about this technique before and had seen this technique applied to understand complexity. And go back to the question, what complexity are we capturing there? I mean, it's amazing. This is an incredible way to look at a very complex process and say, I'm going to make sense of it. It's got latent variables. It's got things affecting other things. We can test them. So really, really good model. So I wanted to share that. We're not going to estimate these, but I wanted to share that picture because the picture says 1,000 words, as we know. And that one does a really good job of of describing that situation. Any questions on that? Did that make sense, what I walked you through there? And I think now, given what we've done over the last 4 days, you have the skill set for me to explain that and you would understand it. If I would have tried that on the first day, you would have said, oh my God, you got up and walked out and said, this class isn't for me. But now, you all have all kinds of new skills. Mad skills, we say, right?
Sir, in this case, some others are not IIT.
Well, so the way we've done this is that there could be some correlation across this. Yes, there could be a correlation across error terms, but the way these are estimated is very different than anything we've seen so far. And the way these are estimated is that this structure implies a variance-covariance matrix. And you know, with all of these arrows and the way this is set up, it has huge implications on what the covariance-variance matrix looks like. And the way these are fit is you compare across the entire variance-covariance matrix the difference in fit implied by this model and the actual variance-covariance matrix. So we look at all the correlations between all the x's, and this implies correlation across all of the x's, x1 and x3 and x1 and x5, and then you compare it. And as you adjust things, it has implications on the covariance matrix, and you just keep adjusting until this fits the covariance matrix. So actually, interestingly, just conceptually, the way this model works is opposite to all the statistical tests we were doing. You know, in all the tests we were looking at so far, we're saying, we want to test if the difference is sufficiently large, and we're hoping it is. We're actually hoping that the difference between two things, like this model and that model, is sufficiently large so that chance can explain it. We want the opposite in these models. We don't want to be able to reject the null hypothesis. So we're looking for differences so small that we can say that the covariance matrix of this is no longer different than the actual covariance matrix. And we keep testing until the p-value gets larger than the 0.05. We say, we can no longer reject it as being different. Therefore, this is a good fit to the data. So it's interesting fit process. But
Also, Abhishek, that some error terms could be correlated, as you said. So that is also shown in the diagram. Like some error terms you have arrows.
Exactly. So that's thank you for that. So look, we've got these error terms connected, and we've accounted for that in the model.
Because you may think that these two variables are not independent to the one.
Yeah. Yep. Question.
Such kind of modeling, is it that where the system involves multiple stakeholders and their interests are different, but maybe they are not aware of each other's process actually. So that's why which is not the latent variables comes up.
So the latent variable. So good question. So the latent the concept of the latent variable is that when you construct a survey and you ask a question, the notion is you're trying to get at something. You're trying to measure something. I mean, whatever it is. Let's say you're asking, someone's perception about public transport. You are trying to get at something fundamental, and the argument is that you probably can't get it with one question. The thing you're trying to measure is you can't measure. It's okay. What's your age? It's easy. There's a thing. There's a true answer, and there's nothing latent about it. But how happy are you with public transport? What do you think about your contractor's management ability? Well, there's probably multiple dimensions to that. Do they manage, conflicts among staff well? That's part of management ability. Do they manage timelines well? Well, that's part of management ability. Do they they give bonuses when people should get bonuses. So all of those things might be thought of as different ways to measure contractor management ability. And so the idea is that that's what's happening when we write surveys and we collect information. And there's a step before this that I didn't talk about. Often we use a discriminant analysis or a cluster analysis to try to figure out or confirm that the questions we thought measured this are they actually measure the same thing. So these things actually are correlated to some underlying construct. And you can use that to help you figure out how to structure these bits of the thing. And then this is all you. This is all what do we think is happening between these latent constructs. Okay. You can't predict it all from it. Can't do any prediction because we don't observe any of those latent variables. But you can explain a whole lot, and that's what it's for. Okay? Yes? So at the time that we did this, the structural equation models and the software could not handle ordinal. Well, no, these were ordinal. These responses were ordinal, but they couldn't handle certain situations really, really well, like indicator variables. But the psychometricians have resolved all those issues now. And so the software you'd get now, you can handle anything. Any binary, ordinal, continuous. So they're all fine. And as you would guess, there's a whole bunch of goodness fit measures with these. There's different ways to assess fit and assess the quality of the models and all that stuff. And that's all in the book. So, all right. Was there one more question? Okay. Yeah. Okay. All right. Cool. That was the bonus thing today. That was that was supposed to. All right. Now. We're on 9. That's exciting. All right. This is a very short lecture, and I probably don't even need to give it because we've already really talked about it. But we'll go through here really quickly. So we're gonna dive right into the modeling, as I mentioned yesterday, and we'll do a few models. So today we're gonna have a lecture, some modeling, and then a lecture, and we're done. Random parameters. Remember, the idea here is now we've always, so far, been looking at fixed parameters, and we assume that everyone has the same effect in the population. And what I described is that if you make the beta not random, we call those fixed or random effects models. And if you make a coefficient, like a coefficient on one of the x's, random, we call those random parameters or random coefficients models. And we now can do these with almost any of the models that we have. So everything we've done, we can add random effects or random coefficients. Okay, so probably 10 years ago, there was, around 10 years ago, probably if you go back to LIMDEP, maybe the version you have. No, probably beyond that. Version 2. You couldn't do any random effects whatsoever. And so it's a fairly new thing. It's become very popular. The reason is that random effects they're computationally much more difficult to do. And in fact, they require a whole different way of doing them than maximum likelihood or ordinary least squares. So we have no concept of doing maximum likelihood fit to random parameters model or ordinary least squares. And so I'll talk you through that. And the lecture that follows on Bayesian models, you'll see even more of this other technique for obtaining random parameters. So we've seen this function. This is the function for the discrete choice model. So what we're going to do, the first exercise we're going to do is a random parameter choice model. So we've seen the choice models and done those. And so now we're going to revisit those and add some random effects and assess what those look like. So we take that, and there's the predictive equation for the discrete choice, which we've seen already and worked through already. It's the ratio of the exponent raised to the beta x and divided by the sum of all of the choices in choice set capital I. Okay? So now we define a mixed model, which is a model with a mixing distribution whose outcome probabilities are defined in this next slide. So essentially, we're just going to define a new distribution that is some function of beta given phi. Is that phi? I think that's phi. Or psi? It's phi. Phi.
We call it phi.
Phi. Okay. So I'll call it phi. So some function beta with phi, referring to a vector of parameters of that density function. So that could be a normal. So it would have two parameters. And if you remember, we're talking about random parameters. It could be a mean and a variance. It could be a gumbel. Somebody asked a question once, why do we use a gumbel or why do we use it was for analytical convenience. And so depending on the distribution, and the number of parameters will be the parameters needed to describe that distribution. And so if we substitute this mixing distribution, so the way to think about that is just that we're defining a distribution for the parameter rather than a fixed value. The way it works actually is we're just going to take a distribution and usually multiply the fixed parameter by it. And so if we combine those, we just get a different looking function with this mixing distribution added into the likelihood function. So mixed logit probabilities are the weighted average of the standard multinomial logit probabilities with the weights determined by the density function. Okay, so if you think of the density function, if the function is equal to 1, the model reduces to the standard multinomial logit. Okay? So you can imagine in this case the distribution would vary from 1 above 1 and below 1 to weight the outcomes. Beta can be observation specific for the effect on the variations on the effect of x on the outcome, or it can be associated with an x. So it can be a random effect or it can be a random coefficient. And we can test. So the beauty of this is that we can test whether there's evidence for a random effect, and we can test whether there's evidence for a random parameter. And if you remember our discussion, I asked the question, what would we test for in the random parameter? In that case, the question is whether the standard deviation of the parameter is 0. And if we can't rule out 0 for the random parameter, the standard deviation of the parameter, that's telling us that it's probably a fixed effect, the same for everyone. And I overheard someone ask, you, Sudeshna, I think, when we were talking about it yesterday, that in practice, and you do these models, very seldom do you get a whole lot of random parameters that you can justify. Often, many of them actually do show up as fixed effects. And you try the random parameters, and you can't rule out 0 for the standard value of the standard deviation. And so we then collapse it back to the fixed effects model again. So again, looking at complexity and asking the question whether individuals behave differently with respect to this variable, or if there's so if we have it as a random coefficient, the behavioral question is, do people respond differently to that x, or does that x differentially influence the outcome y? if it's a random effect, the behavioral implication is, did we omit important things that impact Y that vary across individuals? So there are two different behavioral questions, and that's what we're doing with these random parameters. Okay? So here's the bit that's why this wasn't in the software 10 years ago. The way we do this is different because now we're introducing a distribution, and the way this is done is through Markov chain, Monte Carlo sampling, or some kind of sampling process. We usually in LIMDEP they use halt and draws, which is a Markov chain or Monte Carlo sampling process. And so essentially what happens is the computer randomly draws from a known distribution. So when we specify the multinomial logit with a random parameter, we have to tell it what distribution we want it to use. To say, okay, so let that random parameter be normal, and draw from a normal. And so what's happening, and I'm going to go through this more in the next lecture after, in more detail. But what's happening is we're effectively looking at the model, fitting the model, and then we're drawing from the random distribution, and multiple times, and we're looking to see which random parameter improves the fit. Okay? But we're also constraining the random parameters to fit the distribution that we describe. So we're saying the random parameters need to be normal, normally distributed with the mean of the fixed effect, usually something close to the fixed effect. And the variance we can often define. The variance will be estimated for us. And so it's just assessing fit by allowing individuals to have their own parameter. But those parameters are randomly drawn from, so it has to do it over and over and over again. Assess draw, assess fit. Okay, draw again from that distribution, assess the fit, which ones are fitting well, and then you end up getting a random distribution over all of the individuals. I guess the last thing I'll say on that is we're going to spend more time talking about that process in an hour or so. In LIMDEP, we actually don't know what the parameter is for each individual. We can't dive in. I don't think we might. I'll have to look at that. I don't think we can dive in. I might look when we're all working and find out the parameter that was assigned for each individual. But in the Bayesian methodology, which we talk about later, you can. So it's random. It's not random for the individual. It's random for the population. Okay, and that's an important concept to understand. The parameter itself, if it was random for the individual, then it doesn't really make sense because it's kind of saying, well, then I'm randomly up or down in my response, in the way I treat income. No, you're not. You're either higher than the average or lower than the average in how you respond to income, and that's the point. So for an individual, the parameter is trying to find the deviation from the average that makes sense for you. But for the population, all of those parameters appear to be random. So make sure that's clear. Okay?
So that means basically all the individuals in the population do not behave in the same manner.
Yeah. So let me make come up with kind of an example I think that might illustrate that. Let's say I could know. Let's see. We started class today at 9. Let's say I'm going to guess somewhere around 8:40 was the average time of departure of all of you to the class to make it here today. 8:40. And if I assumed a fixed effect for that my parameter is what time you departed, if I assume that was a fixed effect, that you all left at 8:40, then that would mean that you all have to have left at 8:40. But my guess is that actually is a random parameter. And some of you left at 8:35, and some of you left at 8:45, and 8:41, and 8:39. And so, in that context, I would be saying the average is you left at 8:40, sure, the average effect, but the software is going to look for the deviation that you actually left. But when I look at all of you together at the end, it's going to appear like a normally distributed distribution of departure times. That, to me, looks to be like a random distribution, but for you is very meaningful because it actually captures when you left. Okay? Yeah.
Just out of curiosity, are there models which account for the possibility that their perception about an attribute could change? Like right now, you said for an individual, we say that they would perceive income in the same way. But like, wouldn't that perception vary based on our experience or something like that? Maybe over time, it might vary.
Yeah.
So, like, are there models which can account for it, or is it like something like an endogeneity that we'll have to account for it?
Great question. So the question to answer that question, and the question was, what if a variable changed, like your response to income or your attitude about income or something? So if you put on that research hat in the design of the experiment or the design of the study, let's hope that you don't figure that out afterwards. That actually you have enough, as a good researcher, you have enough insight to because, and I'm guessing that you do, because you're asking the question, so that you would say, maybe in this study, I need to account for the fact that people might change their attitude about income or their sensitivity to price. So I'm going to design a question or a way to capture the change in that. So now I've got a new variable that would capture those individuals that change their attitude partway through. And you have to devise how to do that. So then you can then have a variable that you can include in the model. So, so that's the explicit way to do it. There might be ways to tease it out if you didn't think of it ahead of time, but we're always better off to think of it ahead of time and build it into our design. But yeah, that does happen. Yes, question.
In the same context, like you asked for one particular day, if you check, then it would be a random, it's a normal distribution for all of
Yeah.
us. For the entire week, if we see, so even for an individual, it would be some kind of a distribution, right?
Oh yeah.
Might not start at 8:40 every day.
Yep.
So how do we account for that particular thing if we?
Well, so good point. So if I did it today, you'd each get your parameter. But if I did it again tomorrow, you may not have the same parameter tomorrow. And that's partly why we call it a random parameter. Because even it's not random in the randomly assigned in the moment, but we actually think it's a random parameter. And the justification is that it will be different tomorrow. And so globally it's random. But it's not estimated in the random sense. I don't just assign a random distribution parameter to everybody. I actually try to do it so that it fits the model better for each of you. But it's a good point. And your point comes back to remember my comment about the doctor? And why didn't you make the doctors fixed effects? It's the same thing. I said, well, what's a random effect? A doctor can show up on one day and having a bad day. And so their random parameter is negative, and they're having more patients with infections that day because they were distracted or they were tired or whatever. But tomorrow they show up to work and they're doing really well, and the surgery comes out really well, and their infection rate is really good that day. So in any given day, the parameter could be different, but overall, over time, over space, it's random. And that's kind of why the theory behind it is that it is a random parameter in that sense. Okay. Yeah.
So if you take it for one day, that is a cross-sectional
Yes.
thing, and if you take it over time, that would be longitudinal. So if we include this random parameter model, so even with the cross-section data, that could be a better indication instead of taking longitudinal
Oh, you could do both. I mean, you could do excuse me, longitudinal data, and look at the random parameter over time as well as over space. There's nothing preventing you from doing that. It just depends on what are you trying to understand and learn about the process. But the test at the end of the day for that model I described would be, did you actually all leave at the same time? Or is there randomness among you about your departure time? Okay. So, all right.
So, for attributes such as price, so I think it will be fixed effect for the respondents. If we consider the price, so do we carry out random effects for that? No.
So, good question. The good thing about this is we can test whether there's evidence for using a random effect for a price or not. So it'd be good to have some idea about. We don't want to just go, okay, let's just try everything as random effects, because behaviorally it may not make sense. But you're asking the right question. Does it make sense behaviorally to have effect on price? And as I said before, price, depending on what you're buying, if it's a significant outlay, then price could have random effects because it then becomes a significant portion of income, and people are more sensitive if it's a significant portion of income. Wealthier people are less sensitive to price. So one way to handle that is to actually for large outlays, make it price divided by income. So that's a ratio so that it becomes a percentage of income, and then we can look at the effect of the parameter on the percentage of income, so that people then would the same percentage will respond the same. Anyway, so behaviorally you want to have a good reason to do it. So and I described this. We repeat across many samples, and computer logit probabilities are summed and averaged to obtain the simulated probability. The LIMDEP uses Halton sequence draws, and you can read about that if you want to, but it's just an efficient way to randomly sample those parameters. Just a side note. Some statisticians spend a significant portion of their research in academic life figuring out ways to efficiently draw random numbers from known distributions. And it's a really tough problem. And the idea there's even debates about can you actually ever get a purely random number? Can you generate something, an equation or a process that generates truly random numbers? And the general consensus is that we can't, as humans, we can't actually produce something that's purely random, because they're dependent upon starting values and the starting place and things like that. But anyway, so there's a lot of people that spend a lot of time trying to figure out how to do that well. And we rely on them to come up with good methods to draw that from the distribution that meets our criteria. Okay, so, and this is just a rule of thumb. So the question is, how do we, and I'll spend a lot more time talking about this in a little bit, how do we get that random draw to that distribution to start looking like the one we said it should look like, right? How do we draw from a distribution of those random parameters so that it starts to look like a normal distribution? How many times do we have to do that to get there? And so 200 is usually the number. If you have any questions about that, save them, because I'll go in more detail when we get to Bayesian methods. All right, so let's get out our computers and let's do some random parameter models and see how that works. And the cool thing about this is once you do one random parameter model, it works the same for any model that we've done in the class. Linear regression, counts, seemingly unrelated, all those. So, yeah.
So you said that the limitation of logic model is that that II property. Well, if one probability changes,
That kind of philosophy. The Bayesians say that what we get through Bayes' theorem is actually what we want. And I will be more specific about that in a minute. But the Bayesians, and they have grounds for this argument. They say that actually the classical statisticians are wrong about that they don't recognize the limitations of the output of their models. Where Bayesians, and through Bayes' theorem, get more intuitive results. And I'll talk to you through an example of that. I don't have in the notes. I'll talk to you through an example to make that very clear. And they argue there's much to be gained by using this prior information, and often which comes from prior research. They say that ignoring prior information is like starting from scratch every time we do work. Okay, so let me illustrate. Let me get Bayes' theorem up, and I will then talk through an example. So, Bayes' theorem is derived fairly simply, and just to refresh your memory. So, if you look at the Venn diagram, the Bayes' theorem is derived out of the knowledge of the Venn diagram. So, if you look at the Venn diagram, the probability of B occurring, given that A has occurred, is simply the probability of the intersection of A and B, so that the area that would be defined as both orange and purple, divided by the probability of A. So it's that fraction of the combined area divided by all of A would be the probability that B happens given that A has happened. All right, that makes sense. And you can say the same thing, the probability that A has happened given that B has occurred is the probability of the intersection divided by the probability of B. So using those two, you can rearrange the equations such that you then come up with the probability of A times the probability of B given A is equal to the probability of A given B times the probability of B. The way I got there is very simple. All we did is just recognize that you just move the denominators up to the numerator. So you move the probability of A over and the probability of B over to the numerator. And then you've got the intersections equal, so you can make those equal, and that's how you get that equation. Rearranging that top equation, you get Bayes' theorem, okay, which says the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. Wow, that sounds interesting, but let me explain to you with an example of why that's critical. What we actually get now with classical methods is usually that probability of A given B. Now let me walk you through that. Let's take an example in the safety domain. What we get in the safety domain, let me set up an example. Let's say I want to know, I'm interested in knowing what the probability of dying in a fatal crash if someone runs into a brick wall. Okay? That's what I'm interested to know. Okay? And so it's the probability of death given that you hit a brick wall. So what do you think that would be? Let's say the speed that you're traveling is 100 miles an hour. What do you think the one? Okay? So the probability of death given that you hit a brick wall at 100 miles an hour is close to 1, right? 1 or close to 1. let's reverse that conditional. What would be the reverse? What's the probability that you're traveling at 100 miles an hour, right? So it's death and hitting a brick wall. What's the probability that you hit a brick wall at 100 miles an hour, given that you died in a crash? What do you think that probability is? Close to 0. So I use that example to say that the reverse conditionals can be very different in probability. Very, very different in probability. And the reason that's relevant is because when we use classical frequentist models, what we're doing, in effect, is calculating the probability of the betas given x. Okay? So we are looking at the probability of the betas given x. The reverse conditional is the probability of x given the betas. And the argument, and this will come up again as we go through, the argument by the Bayesians is that the conditional that we really want is provided by Bayes' theorem. Bayes' theorem gives us the conditional probability that we actually are interested in, whereas the classical conditional is not the probability we're interested in. Okay?
So,
Yes.
in classical, it is basically the probability of the x given beta, right?
Yeah.
Like, what is the probability of getting the data of the sample
Yeah.
given this is our data?
Yeah. So I'm going to rephrase this and put it in terms of data and the parameters, right? So the Bayes theorem down below. If you just go down below, Bayes' theorem says that what we actually want, what we're most interested in, is the probability of the thetas given the data. Given the data we have, what's the probability of the betas happening? And the reality is, what we get from likelihood or frequentist-based approach is not that. We're getting that other probability on the numerator on the right. We're giving the probability of x given theta. So all the methods we've done are conditional on theta. What's the probability of x? And that's not what we want. We want the other one. And so the Bayes argument is that philosophically is that through Bayes' theorem, we can convert the likelihood, the data that we get, that we normally work with, multiply it by the probability or a prior on the parameters, divided by that denominator there, which is the complicated bit, and we can get the posterior, which is on the left, the probability of theta given data. So think about it. Everything we've done, we actually want to know how can we believe in the betas given that the set of data we have. And we've actually not been getting that. We've been getting that other reverse conditional probability. And all the classical methods are built up around that other conditional probability. And we kind of ignore it. And the Bayesians say, you frequentists, just ignore the fact that we have the conditional probability that we don't want. And through my illustration with the brick wall and fatal crash, the conditional probabilities can be quite different. So let me give you another example just to cement this concept. When we collect crash data, what are we actually getting? So if we do a look at a crash study with speed, and speed is one of our x's, right? And we have a model where we have speed, and we are looking at the effective speed on crash probability, say. Crashes on motorways or something. What are the data that we collected that we're often using to estimate those models? Data that were conditional on the crash having occurred. So we are trying to make inference on a set of data where the only data we have is conditional upon a crash. Okay, so when we look at speed, the spective speed is conditional on the crash. What we want to know is we don't want to know the probability of speeding given that a crash occurred. We want to know what's the probability of a crash given that speeding occurred. And we can't actually answer that with the models when we collect them and that kind of data. And we pretend, and we just ignore it, and we just pretend that we can. And so we would have to and that's actually a problem with the data, the way the crash data are collected. But another way of illustrating that reverse conditional probability is that we sort of wave our hands, and a lot of people will do these speed models and say, therefore, speed has an influence on crashes. And we actually say, no, actually, it's not quite right. You can't prove that speed influences crashes. We have no idea what happening with speed with all the non-crashes. So it's another illustration of this reverse conditional probability. All right. So the rest of this equation is that the probability of x given theta is the probability of is what we call the likelihood, and that's what the classical. That's what we have been working with in this class so far. And the pi of theta is the prior. That's what the Bayesians say. That's what we should bring to the table as prior knowledge. And if we use that prior knowledge times the likelihood in the numerator, we can get the posterior. The problem is we have this ugly denominator, and it's the marginal probability of x. The denominator in this Bayes theorem has been the problem, and the reason why we haven't had Bayes theorem working in computational models for a long time. We don't have an easily closed form solution to solve that denominator. It's an integration problem. And it's a very difficult computational problem to solve. So that what we've done is there's generally three approaches to solve that denominator. One is an analytical approach. And that's, if you go back 10 years and look at Bayesian models, that's what you'll see in the literature, is that the statistician saying, well, we can do this Bayesian model, but as long as the distributions we're using in the model are conjugate distributions, sort of like the same family of distribution, so analytically they work well together, we could solve it, but that denominator. But anything unusual in any way, you couldn't solve it. Then there's the numerical approach, and that's what we use in the maximum likelihood, is we solve a function, we look for a maximum, and the limdep is in the back doing this numerical process to find and search this function. If you remember, some of you got an error message that said the likelihood function is flat. So it's doing all its work and it's gone up. It's flat. I can't find the maximum. So that's the numerical. And that approach for these models is also very difficult. So where we end up is this, we use this last approach, simulation, which is what we actually use to get the random parameters in the last model. It's a very, very powerful approach for solving these kinds of problems. And I would argue, and we do in the book actually, that it's the reason a lot of people are using Bayesian models now is not because of Bayes' theorem. It's because of the simulation, the strength of the simulation in the estimation process. And I'll illustrate that to you in this lecture, why it's so interesting and so powerful. So that's how we solve it. So we use simulation-based approach. And the practical version that we use in these simulation processes is this version here. The probability of theta given x is proportional to the f of x given theta, or the p, or you can replace that with p, the probability of x given theta times the prior of theta. That expression is what's used, and the thing on the left we call the posterior credible interval, and Bayesians call the posterior credible interval. So kind of like a confidence interval. A confidence interval is obtained from the likelihood, and classical methods, the posterior credible interval is obtained through Bayes' theorem. And that's why you'll see different terminology. And Bayesians would never let that terminology collapse to confidence interval, because they would say, no, no, no. Confidence interval is with that inferior, reverse conditional. We have the good information, the good bits, and that is obtained in a posterior credible interval. So, and so that's what we would call it. So what we'll be seeing in these results are, instead of confidence intervals around things, we'll see posterior credible intervals. And that's the terminology you would normally see. Now, I know a lot of this is not making sense yet. Probably it's not sinking in, but it will as we start to go through the example and we start to narrow in. But before we can get to the example and see how this works, I need to tell you how the MC works. So you just kind of understand what's happening in the computer when these models are solved. Okay. Everything we've done so far, we have done either analytically, least squares. We just solve some equations. Or maximum likelihood, we use numerical searches, and we search a function. Now we're doing simulation, and I want you to understand how simulation-based estimation works. So we are now simulating from known distributions to solve the problem. I'm going to walk you through how that works. Discrete time intervals, so time unit 1, we draw random samples, we do some computations, and then we draw again, and we draw again, and I'm going to walk you through that process. And so we draw, we assess, we draw again, we assess, and we keep drawing until we get a distribution that's like what we want. Conceptually, I want you to understand, so the Markov chain Monte Carlo, the sampling is what we call a random walk process. And we are going to randomly draw from some wide possible set of values. And what we're going to do is we're going to take a draw, and then we're going to take another draw maybe over here. And we're going to assess if this draw over here is getting us closer to a good fitting model. And if not, then we might take our next one over here. And we're going to keep randomly drawing in a random walk process until we start sampling from a known distribution that also satisfies improving the model. And I'll walk you through step by step how that works. Let's just talk about the properties of Markov chain Monte Carlo. So statisticians, a number of them, spend a lot of time on assessing how these random draw processes work. It's actually a big challenge to draw from. So what we're trying to do is draw from randomly to get that posterior distribution, given the model we've specified and all the distributions that we've specified. And I'll compare and contrast to how we've done it before and how we're going to do it now. So these are properties that the people in mathematical statisticians focus on in assessing how these Markov chains work. We're not going to focus on those. The Gibbs sampler is a particular Markov chain Monte Carlo sampling process that converges to the solution we want very quickly. And the solution, when I say the solution we want is one that gives us a good model fit, but also results in parameters with distributions that we specify ahead of time. All right, so this is how they were discovered, and there's Metropolis Hastings MCMC algorithm that was originally used to do a lot of the sampling, and the Gibbs sampler is a special case of the Metropolis Hastings algorithm. All right, I'll walk you through this numerically, and then I'm going to walk you through this in words. So in this is the general process that happens. So the x's in this case are not the x's that we've been using in the x's are the betas. So in the sampling estimation, what we're focused on estimating are the parameters of the model, the betas. And so for example, if we had over dispersion, we would be interested in that alpha, that over dispersion parameter as well, alpha, right? So all the parameters in the model we're interested. So these x's refer to parameters because that's what we're trying to sample from. So the way it works, and I'll just show you the equation. So the way the sampling algorithm works is that we draw a sample, an estimate of x1, which might be, let's say, beta 1. But x1, we'll just keep them x's to be consistent, but they're the betas. At time t equals 1, t plus 1. x1 at times t equals 0, we give the sampler, when you estimate your model, you have to say, here are the starting values for all of your betas. You have to tell it. So WinBugs requires you to say, okay, you've got 9 betas in your model. Tell us where you want the Gibbs sampler to start, the starting values. So t equal 1, or x1 at t plus 1, is the first random draw in the algorithm that started from, you gave it, say I give it the value 5. And say, okay, now I'm going to try 7. So my first value for beta naught was 5, and it's going to draw randomly and maybe pull out, for example, a number 7. It's going to pull out number 7 conditional upon all of the other betas in the model, which were specified in the starting values. So I've got time equals 0, starting values. The first step, first draw from the sampler is updating the estimate of beta naught. And then it's going to fix beta naught, and now it's going to move to beta 1. It's now going to take the second draw from beta 1. It's going to leave beta naught, what we just updated. It's going to use all the 0 starting values for all the rest of the betas. And it's going to keep going one by one through all of the betas and updating the estimates of beta. Okay, so 2 things are going to happen is that when it draws that next sample, it's trying to draw a sample that's improving the overall fit of the model, right? So we had R squares, we have these goodness of fit, and these models have their own, but similar to that. It's trying to improve so it's hoping that the random value it pulled for beta improve R squared. But it's also ensuring that the distribution of what it's drawing is normal, if we specified that the betas are normal, which is a reasonable assumption. So it's doing those 2 things simultaneously. So it's actually a difficult task. And that's why statisticians have spent a lot of time figuring out, how do you do that? How do you invent a random walk or a chain sequence of random numbers that both help you satisfy the goodness of fit of a model, but also satisfy that the distribution of those numbers as we keep sampling approaches a distribution that you know. Because that's what we get when we do our other sampling process. So, so in essence, the current estimates of the parameters are obtained using full conditionals of the most recent estimate of all the parameter values. For example, a posterior estimate of beta naught 2 would represent an estimate at time t equals 2 and represent an update conditional on the all current values of the previous betas. Right? So you can see this process. We're slowly updating our estimates of beta based on the actual data we have and the way we've specified a model. Samples are positively correlated, so each sample, if we look at them over time, would be correlated. And upon convergence, the sample of parameters represents the posterior density of the model parameters. So this process meanders all over the place in the beginning. Our estimates of the betas could be really wildly wrong. And it's trying to find its way to settle in on the parameter. So I'm visually showing that. So we have no idea where the beta 1 needs to end up. And I might go here, I'm getting information about fit, and I might come over here, and I'm going to sample over here, and then all of a sudden I'm going to keep sampling, and I'm going to narrow in on the mean of beta and the variance of beta over here, but I started over there. Those values are terrible. And that's why in the sampling routines, we have what we call a burn-in process, where we let the sampler draw randomly and let it find its settling point and throw out all the garbage, because we don't want to include that in the distribution of beta. Because the distribution of beta, these are a real distribution we're creating through the sampling. This is very different to what we've done before. We just do the numerical search. We assume things are random. We test that assumption, and it all worked out. So you're probably all thinking, this seems like a very complicated way to go to estimate these parameters. You'll see why it's so useful in a minute. But at this stage, I'm just trying to get you to understand how we estimate these models. So easy models, we might throw out the first 5,000 estimates of the parameter. So that's how long it can take. And that's an easy model. We'll throw out the first 5,000. So that this thing I'm showing you, it might meander all over the place. Because it's not just this is beta 1. Beta 1 changes, but then beta 2 changed, and beta 3 changed, and beta 4 changed. And based on those changes, you might have feel like you're narrowing in on the right solution, but now you change these other ones behind me, so all of a sudden, well, no, given that those have changed, now this one's not very good anymore. So it's simultaneously trying to find the right home for all of those parameters. Complicated models might go up to 10 or 50,000 iterations that you just throw away. And so what we're essentially doing is those distributions of beta are formed by the sampling, and we collect them. We collect the estimates and the distributions from the Markov chain Monte Carlo chain, and those are end up being the results. So when you look at our outputs that we've seen so far, we say beta. It's been really easy. The fixed effect estimate of beta is this, and the standard error is this. We computed those. In the Markov chain, we're actually going to collect the samples and say, this is the distribution of those samples. The mean of those samples is here. That's the estimate of beta, and this is what the distribution looks like. We actually created, through the sampling, those distributions. And so here's some general views. Problems with fewer parameters converge more quickly. Convergence is faster for smaller data sets. Variable expression may affect the convergence, et cetera, et cetera. And conjugate priors converge more quickly. So the more complicated the model, the more. So I had, so these, I mentioned that we had a Poisson, simultaneous Poisson models that we're doing. If you remember, I mentioned they were simultaneous Poisson. We had 12 years of data, so they were panel, and we had spatial effects. So we had a fairly complicated model, and we used Bayesian model to do it. The runs were taking about 8 hours. So the sampling process, the burn-in iteration, I think we were doing 200,000 burn-in iterations, throwing all those away. And to estimate the models in the Bayesian, it was about an 8-hour run on a modern computer. So these can take and that's harking back to the old days, what we used to do for maximum likelihood and the methods we're using now, because computers were so slow. But so that gives you a sense of the kind of computational stuff going on for complicated models with these, because we were having to draw from these distributions, and it takes a lot of time, or it can. So let me walk you through a conceptual example. So this is really clear, and then we'll end up, and I'll show you an example of the output of one of these. So here's the linear regression model. We all did that. We estimated beta naught. I'm making it very simple. We estimated beta naught and beta 1. Ordinary least squares. We just calculate. We just have an equation. There's a linear. Actually, we even showed simple algebra equation that gives you a direct solution for beta naught and beta 1. So easy. But in this approach, it's different. So previously we estimated the beta vector using analytic techniques. We tested whether the assumptions are true and relying on asymptotic sampling. So we estimated those analytically, and then we say, okay, let's plot our residuals to see if they seem to meet normality conditions. In Markov chain Monte Carlo, we do that differently, as I've described. And so this really, this kind of describes what I just said, is that we'll take the first value, and these are not in your notes. I added these last night and this morning, so sorry about that, because I was reading through and I thought it'd be nice to add one more description of how this happens. And so after each iteration through the equation, say after 30 iterations, the betas start to look like the distributions that we want them to look like. Through the Gibbs sampler, the pseudo-random sampling does a random walk after successive draws, and the model fit is improved. The posterior distribution approaches the specified distribution, and we then draw on those. You can take up to 50,000 for complicated models. So the last line is probably the thing that what happens here, and that can get very complicated, is that Bayes' theorem itself means that we're going to have a distribution of the data themselves, or so the beta that comes from influenced by the data, but also the prior distribution. And the prior is something we specify in Bayes' theorem. So we're actually going to have two distributions working and influencing each other, and I'm going to show you how that works. So if you remember Bayes' theorem in your notes, the right-hand side numerator is the likelihood, which is all of the x's, and a prior. Okay? The prior is going to be our statements, can be subjective statements about what we think the parameters should be, which is very interesting. All right. There are goodness of fit measures, and I'm then going to walk you through these examples. So deviance information criteria, and just like other models, we assess the goodness of fit of models. I'm not going to spend a lot of time on these, but the Bayesian information criterion, essentially these are just like equivalent to, say, R-squared and penalized measures, where we measure how well the model fits to the data. So let me walk you through an example so you understand what's happening. Okay, I'm going to use data that we've already seen so you can see how these models work. All right, here are the data. You've all seen these data. We've looked at these data. These are route choice, right? The arterial two-lane road freeway. So purposely use data that you're familiar with. We're going to I've estimated this model in a Bayesian framework. All right. Here are the results of the Bayesian model, Bayesian parameter estimates with non-informative priors. Now, so there's a thing that a phrase that we use in describing the priors, and the Bayesians use this word uninformative or non-informative or vague. They all mean the same thing, as describing that the prior information you bring to the table isn't that informative. It's not going to influence what happens in your model. If you have a Bayesian model and all of your priors are uninformative, it's exactly that. There's no information that's useful. Then you'll get the same exact result as you would in a classical regression model. So here I've done is I've estimated a Bayesian model with completely uninformative priors. What do I mean by uninformative priors? Right up there on the right-hand side, that all of the betas, the prior I bring through Bayes' theorem says that all of the prior information tells me that the betas should be normally distributed with mean 0 and variance 10,000. What does that look like? Right? It looks like what I'm saying is that I have no freaking idea what beta should look like. I'm giving a prior that has almost no specific information about what it should look like. It could be minus 15, minus 10,000, plus 10,000. I have no idea. Almost, I mean, I could have specified a uniform distribution between minus 20,000 and plus 20,000. Right? That's almost the same. So no information there. And what you see is the estimates, and in parentheses are the estimates from maximum likelihood. Okay, and they're pretty close. One thing you should notice is that on average, the Bayesian estimates and the standard errors are a little bit larger. So the Bayesian sampling is less precise. So you sacrifice a little bit in precision by using a Bayes model. And you can see they're just slightly, on average, they're slightly larger standard errors through the Bayesian sampling process. But the coefficient estimates are all very close, right? So they're equivalent, and if you have non-informative priors. But here is where the strength of Bayesian method comes in. Let's look at the model now and the coefficients under different priors for the ratio of beta sine 3 to beta vehicle age. Well, that's kind of weird. You can actually, and what I've done here, I've actually signed prior on a ratio of 2 parameters. Wow, we can't do anything like that in maximum likelihood. In fact, you need Bayes' theorem to do that. And what I'm saying there, so I have three models there. The top is the uninformative priors, mildly informative prior, and informative prior in the bottom. And what those correspond with, you can see them. The top is, again, I assume that ratio in the top one is normally distributed with mean 0, variance 1,000. So the ratio of those 2 parameters is very vague. In the second model, I've assigned a prior that says, no, I'm going to assign a prior of minus 5.82, very specific, with variance of 3. And in the bottom, I say, I'm going to assign a prior on that ratio of minus 5.82 and a variance of 1.15. So let's look at the bottom one. That's the power of Bayes' theorem right there. It's saying, I'm going to let the data estimate a model. I'm going to estimate a model using the data I just collected. But I'm bringing some information that I've known from some other study or some knowledge that the ratio of those 2 variables should be around 5.82. I have some reason, and the assumption is you have some really good reason to believe that that should influence the result of your model. Right? Maybe 10 prior studies have been done on that ratio, and if you combine all those studies, their average minus 5.82 effect, and the variance of those studies is around 1.15, and you want to include that in your current estimation. So what happens? What you see in the results are the estimates of the beta sine 3 and the beta vehicle age with those priors that come out. So they get shaped in each of the estimations more and more by the prior. So you see in the top model, the beta sine 3 is minus 0.38. And so you could compute that ratio of those 2 because that's what the prior was assigned to. And then it becomes, in the next model, 0.45, and in the bottom, 0.48. So it's more and more shaped by the prior because it's more precise each time and more specific. That's nothing we've been able to do at all. And any of the models we looked at there include some prior information. Wow, we have no way to do that. And Bayesians say, what? Wait. We're not starting from scratch every time. We have information. We could have cases where we think something should influence our results. So those parameter estimates reflect what we know from the current study as well as what we bring from prior studies. And the Bayesians would say that is our current best information because it includes all this good work that's already been done. And you classical statisticians that use maximum likelihood have no way to do that. No way whatsoever. You ignore everything that was said before. So this illustrates exactly what Bayesians are trying to achieve. And here are the posterior credible intervals. This is output from WinBugs. I go in and I sample what the sampler produced for those marginal rates of substitution for those ratios. Okay, so there you can see the three different marginal rates of substitution and how they differ across the models. So let me say this and then we'll kind of summarize. So the coefficient estimates change in proportion to the certainty provided by the prior information and the difference in the mean estimates. The way to understand this conceptually is that the final posterior estimate is going to be really weighted by the variance of the difference in the variance between the data you have and the prior information you bring. So let's say if the variance of the prior is the same level of variance of your data, then they'll have equal weight in influencing the parameter value. If the prior is twice as efficient, it will have double the weight in influencing the value of the prior. So Bayes' theorem is really cool because it says, well, the more precise the information, the more weight it should have. Right? If your data are kind of dispersed and random, but what they did before was very precise, well, that's going to have more weight in influencing your parameters. So that's how that works, and that's specified by Bayes' theorem. They're similar when you have uninformative priors, you get the same result as you would with maximum likelihood. And then that begs the question, well, why would you do it? Why would you go to all that effort if you assume not informative priors and get the same results as you would in maximum likelihood? The interesting part was, I'll make a statement, is almost all the work we see in transport assumes non-informative priors. And there's a fair amount of work using Bayesian models. So my question to you is, why do you think people are going to all this effort to use Markov chain Monte Carlo estimation with non-informative priors? Because if you're using non-informative priors, you're really not taking advantage of Bayes' theorem. You're kind of saying, Bayes' theorem, I'm not going to use it because if you get the same results as maximum likelihood. So why would people, any guesses about why people are going to such efforts? Why did I do the Poisson models with random effects or random spatial effects and panel in the Bayesian framework? Well, I did do it to get the distribution of beta, but the reality is I can't find software that can estimate that model for me. Because the models, some of these models that we start to look at become so complicated in the log likelihood function, and they're not built into packages. Again, they can't find it in Stata and SPSS, but you know how to specify the model, but we don't have models that have actually been coded to do. So what we're seeing, and why we're seeing an explosion of Bayesian models, is because the likelihood functions or the specifications of the model are so complex that we don't have the tools to do them. But Markov chain Monte Carlo sampling, as long as we set up the model correctly, we can estimate the models. They just take a lot longer. And so most people are just throwing away Bayes' theorem and saying, well, we're not going to use anything informative, and we're going to estimate the models, but we're going to be able to do complicated models. And that's exactly why we did the simultaneous Poisson with panel and spatial effects. Couldn't find it. Couldn't find it anywhere. But that's the model we needed for the data that we had. So we can do it in R, in the Bayesian framework. So that's what we're seeing happening, and that's why people are using these methods.
Simon,
Yeah.
One more thing, I think in our paper also you mentioned that that it is still better than doing that frequentist model.
Yeah.
Basically, if you have small sample, then we are the approximation in frequentist is often normal, but here at least the data is deciding what should be the parameters.
Yeah, absolutely. Absolutely. But that's really essentially why these models are becoming popular, is because the complexity of the models that we're trying to fit these days have outstripped most of the software packages that can estimate using classical or frequentist methods. And so the sampling-based estimation works pretty well. And that's what we're seeing, why we're seeing just a whole bunch of these Bayesian models showing up. But you understand that the Bayesian part of it can actually be very useful, because there could be really good reasons why you would bring prior information into your model estimation and influence your parameter estimates and what you get out of these models. And so still looking for good case studies to do that with, and get published and do some work on that. And that's why I mentioned meta-analysis, because meta-analysis is a good example of how you would do that. You could do a meta-analysis of what people have found on some effects, and then bring the results of that meta-analysis into as priors in the model, and update. So, any questions? So that's the last slide of 5 days of statistical modeling. It's been a great journey for me, and I hope it has been for you. Very, very enjoyable. Has anyone here not learned anything? I hope that you've all learned a lot, and I know you all came in with various degrees of background in stats, but when you immerse yourselves in statistics and modeling for the time that we did, hope that you now see that really this is about complexity and understanding the complexity and the process that has generated the data that we're interested in, and trying to capture all those nuances and complexity in the model that we use to then convey to an audience about what's really happening in the process, to forecast future events and those sorts of things. So I do hope, sincerely hope, that all of you feel like you've upskilled in your ability to understand data, make sense of data, and do all those great things. So thank you very much, and thank you, Sudeshna. It's been a wonderful journey and a wonderful time here at IIT Kharagpur. You have a wonderful program and university. I've had good fortune to tour around and see what's happening here at the university. So it's been a really great experience for me. So I will definitely be back. And thank you to the head of school, head of department, for hosting me. We've really enjoyed my time here.
Thank you so much, Simon. And I think everybody would agree that we gained a lot from your this 5-day teaching. And I requested Professor Reddy, our head of the department, because the first day there are a lot of things going on, some PhD defense and all. So I would like Professor Reddy to
I think there was statistics going on. She wanted a non-statistician to be there.
And Professor Reddy, there are some students from outside, other IITs and NITs. So
Good afternoon, all. And then at the outset, I'm sorry that I could not be there at the inaugural session. I think a few things were going on that time, so I don't recollect where I had to go. But I could find time to join dinner with Simon. I already met Professor Simon twice, initially when I came to the department, then during the dinner session.
We had a very wonderful discussions, and I was also getting feedback. He was spending a lot of time. I don't know whether it was too much time for you, more than the time that is allocated. I think he was going to everybody, trying to solve your tutorials for you and all those things. Thank you, Professor Simon, actually for accepting the invitation of Sudeshna and then being here, spending 5 days. It's not easy to go out of your place and then spend 5, 6, 7 days outside. That we understand. So you people have been discussing about statistics. As I said, I do not understand. The only statistics I ever done was because I used to teach traffic engineering initially because we didn't have a teacher. So only that mean confidence levels before and after evaluation and maybe a couple of other things is what I did. I could not lay my hand on that statistics book which I once read. I always take comfort by reading that introduction. I'm not recollecting that statement. I think many of you might have seen that, where I think the book actually gives me an impression one doesn't have to do statistics because at the end of that, I can say anything. Because you are statisticians where I do not see any trend, you show me trends. Where I think I found a trend, you say that's not the correct trend. Right? So I think this is something that I could never crack and I could never understand. Maybe I think you need to have a special skill to do statistics. But I think we have people. I think I was coming from a synopsis seminar. Bayesian thing is what they have been discussing about.
Water resource.
Yes, if you know Professor Esquerra, when he left, he handed over a number of books to us, and then maybe 50 years back, he was teaching Bayesian statistics. I don't know whether he was practicing that time. So thank you for enlightening our students who have come from IT Kharagpur as well as outside. I don't know how many outside students are there. It is too late to welcome you, but I welcome you. I hope you come back again. Because I don't know how many of your PhD students, master students. Those of you are master students, please come back and then join for PhD program here. You have to go through a written test in entry. So I welcome you all to come back again. And I wish you a very comfortable journey back. And then I'm sure we'll have a lot of future interactions. Thank you.
Yes, thank you very much.
Professor Reddy, I would like you
Yeah,
to
memento to the head of the department, memento to the visiting guest.
Yes.
No.
No, to the another head.
Thank you. Thank you.
And Professor Reddy, that day we could not, invite, like Helly's flight was delayed. Helly, if you can come here. So, you could not meet her because her flight was delayed that day, on the day of dinner. So, I request her to come. And if you can hand her the history of IIT Kharagpur.
This is something I would like to do. Welcome to Kharagpur.
Thank you. And now, Simon, we have to hand the certificates to the participants. So,
Yeah. Yeah.
Simon can do that.
Yes.
Yeah.
And we'll call the names. And
Yeah.
we can. Okay, Kuldeep Lohani. Kuldeep, you, right? Yes. Naushad Ahmed. Nasha.
Did you want to take photos? Or? Yeah. Yep. So your turn on. Yep.
Naushad is not here. Priyadarshini is also not here. Roshan just stepped out. Yeah, he's coming. Rima Bera. Yes.
Oh. So how? Yeah. There we go. Yes.
Preeti Saini.
Thank you so much, sir.
Congratulations.
Shankara Fani Kumar.
Yeah. Great talking.
Ravi Maurya. Saurav Dandapat.
Good job, Ravi.
Shivangi.
Good job.
Shivangi Singh Parmar.
Congratulations.
Somnath Bhui. Shuchismita Naik.
Good job. Nicely done.
Sudeepa Chatterjee. Sani. Sani Bansal. Shuparna Dashgupta. Sushant Kumar Sial. Shoma M. Shoma. Soumya. Oh, Soumya. Okay. Satyajit Mandal. Vikas Nimesh. Vikas. Vikas Yadav. Zehra Mehdi. Manoranjan Ghosh. Manoranjan. Sai Kiran. Annam Sai Kiran.
Thanks for the good questions.
Abhishek Chakravarti.
Thanks a lot.
Bhaskar Pal. Dipanjan Mukherjee.
There's only a few students that didn't ask questions the whole time. And there's only maybe three. Every single one has engaged. It's been really good. Oh, absolutely. A lot of questions.
Sir, and I think these 5 days is not sufficient to discuss all those things.
Vipul Shaha. Srinivas Gandhi. Dipanjan Na. Gaurav Thapa.
Thank you.
Gaurav. Gauri Arun Kumar. Hirak Chaudhary. Kanishka Ghosh. Oh, Hirak Chaudhary.
Good job.
Konishko Ghosh.
Nicely done.
Kannadasan D. Kuldeep Kumar Maheshwari.
Now there are lots of good questions, Guy. Yeah.
Saddam Hussein is not here, right? Meenu Francis.
Nicely done, Meenu.
Navanita Roy.
You're welcome, Amrita. Good job.
Nandan Haridas.
You're welcome.
Thank you so much, Simon.
Yeah.
Yeah, we'll take a group photo after you finish up, that feedback form. We'll step outside and take the group photo. I know that. And the outside students, who came from outside, after taking the group photo and submitting this feedback form, you please stay back. Okay, the students who came from outside, the IIT Kharagpur students may leave after submitting the feedback form and taking the group photo. The students who came from outside, I request you to please stay back. Okay. And actually Roshan, another student, he went for some other logistic issues. So he will, we'll hand him the certificate, and that time you please take another photo. Okay. Otherwise he'll be sad. He was here. Roshan.
So you're trying to do it outside?
Yeah, the group photo, probably this is,
Or you want to do it inside?
No, I think that one is there. Yeah, with this one.
No, if the ambience inside is, you can take this.
Okay. But we're trying to do it, but it's
Very crowded, yeah. Yeah, they were just really, really engaged students, and really, really great questions, and they were clearly always trying to relate what we're doing to their own research programs. Well, of course, but it happens sometimes, and this is the 5th time I've taught it in this kind of setting, and this was one of the better ones. Yeah, so I'm very impressed by the students. So.
So we'll be meeting again at TRB.
Yes.
Yeah.
Yeah. Absolutely.
Yeah. We will have a small discussion again.
Yeah. Did you enjoy it? Yes.
You are very kind and very energetic. You are very energetic.
What's that?
You are very energetic.
Okay. Oh, it's going in there, yeah.
It's cutting in and out, but still.
পড়াই আছে হ্যালো হ্যালো হ্যালো